Okay, so tracing tables with a recursion, the big thing to remember is, I'm just going to use an example here, but if you have, say, the divide method, which takes in a natural number, or let's just say it's divided by 2. There's a way that you can do a recursion on that. The biggest thing to note when you're, I don't know why I started so high, but is looking at the contract. So when you get to the part in the tracing table where it's, say, divide 2, and then you pass in n, assuming that you've done some sort of divide by 10, and then you've divided it by 2, and then afterwards you're going to do something like multiply by 10, and then add the last digit. The biggest thing to note is that on this right side here, you essentially just assume that whatever the contract for divide by 2 is, it works correctly. So if divide by 2 says that it ensures, so this is n is equal to the old value n divided by 2, and n, when you get to here, is 124. After this call, you can make as many assumptions as you want that the code worked as intended. So 124 divided by 2 is like 62. Yeah. So you assume that the code worked correctly when you called it in the tracing table. A lot of people end up trying to write multiple recursive tracing tables, which is not the case. If there's no loop, like no while loop, and it's just a recursive call, you should only have one set of numbers throughout, because you're starting from the top where the initial values are the initial values. You're treating this as if it was basically a static method, except it's not. It's the recursive method. But the way we treat it is that it's a static method that will return the correct value to you, and then you have the resulting values, which means that there should only ever be one column. If it's some sort of loop, though, like a for loop or a while loop, that's when you would have multiple iterations to the loop. And then remember, because some people forget, but let's just say that we have I equals 5, and then we have some sort of if statement where if I modulo 2 equals 0, we do one thing, else we do another thing. Let's say this is I plus plus, and this is I minus minus. When you are on the right side talking about the state of things, like the mathematical variables, if you skip over an iteration, so in this case, since I is 5 here, I will be 5 here. This is not the general formula, but it's going to get the point across. But since we don't go into this if branch, you must include a dash here. So I equals dash, because you're skipping the iteration through that part of the code. So this will be I equals 4. This way, if I ever want to look at a statement of code, if I ever want to know what is the value of I at this point of the code during the first iteration of this loop, so this whole thing was like encased in like a while loop or whatever, like that. Then I could do that by just looking at the first column. I could say, okay, the first time through the iteration, I is 5, and then it's 4, and then it skips over this iteration here. Now, let's say we went back again, and it was 4 this time. So we go here, we can cross out 4. This time, since I is even, we go into this, so this becomes 5, and this becomes blank because we skip over that iteration. And in an actual code, this, I think, yeah, this would be an infinite loop. So if that ever happens, you can just say infinite loop. And that one. Does that answer your question? Okay, cool. What else? Yeah. Yeah. So, my eraser. MVC, or model view controller, is a way of separating out tasks. so that nothing has to be entirely contained within a singular Java class. So we want to separate out the concerns of parts of the files in Java so that they don't have to worry about everything. And that breaks down something like this, where we have the model. That's a bad marker. We have 3 red ones. You have the model, which is in charge of keeping track of all of the mathematical states of the variables. So if you remember, we talked about the difference between a concrete value and a mathematical value. It's a good way or a good proxy to think about how this works. So in Java, the concrete value of, say, I equals 5 would be an integer with the value of 5. That is modeling the mathematical value of 5, the integer 5, which just exists in math because it has always existed. The model is a way to represent the abstract value of what is being displayed by the view. The view is everything that you actually see. So everything that is shown to the user is contained within the view. That is all of your those swing bucket buttons, panels, all of the other ones that you can have, buttons, panels, inputs, scroll panes, that kind of stuff. In between them, and to mediate everything, is the controller. So the controller has a reference to the model. So the controller can update values within the model, can update the mathematical model behind the concrete values in the view. The model can tell the controller what its values are, so it needs a reference to there. Then the controller can tell the view what the values of the mathematical model of, say, a calculator input pane is. And then the view can tell the controller when things have happened to it, such as buttons being pressed and that kind of thing. The general way that it pans out is that the view will tell the controller when something happens. So these are called events. Events happen to the subject of, say, a button or a scroll panel, and it will go to the controller and it will say, hey, I have a button on me somewhere that just got pressed. I don't know what to do about it. And the controller will be like, well, I know exactly what to do about it. I have to update the value of your input scroll pane to be 1 more than it was. And so it'll go to the model and it'll say, hey, can you update that mathematical representation of the top panel that's on the view? And then the model will do that. And then you have that method called update view to match model, which will essentially take all of these mathematical representations in the backend and pass them to the controller. The controller will then propagate them to the view. This is similar to a concept in traditional software engineering, where you have a front end and a back end. So I'm trying to think of a good example, but like all of the images, that's a good one. All of the images on, like, say, your Instagram feed, they are both stored in some database somewhere. They're not all stored. The entirety of Instagram is not stored on your phone. Hopefully that's not a shocker, but there's a big database somewhere, which is the model of all of the Instagram photos. When I say click on my friend's post, the controller goes to the model, says, hey, you have an image in your database that your friend posted. I need that. It propagates it to the view. So there are technically 2 versions of the image that exist. There is the concrete truth, the model, and then there's the view, what you can actually see. So there's just separation of concern. This is the back end or the ground truth, if you want to think about it that way. And then this is what's known as the front end, which is everything that you can visually see. And then between them, you have some sort of middleman that's in charge of caddying the information between them. Does that make sense? Or okay. What else? What else? What else? Okay, then I'm going to go through all of the data structures because that was a common thing. So we spent a good portion of the last month going through all of the fun little data structures that OSU CSE provides. And there's a bunch of different things that set them apart and make them unique. So we are going to make a big chart. Huge chart. Yeah. Yeah, so any data structure that you need in order to write a method will have API documentation on it, on the back, as they have in the previous exams. And if they don't, I believe, give me 1 second. If you need to look up the JavaDoc API for anything else, your instructor will have a browser open on a computer in the classroom for you to use. So if you're writing code and then say that you want to look up the API for a stack method, you can just come up to me and ask me what the method is, and I can look it up for you. So yeah, keep that in mind if you need it, but everything should be there. And if it's not, you can ask. Okay. So we can start. I'm going to start it over. Oh, that's a good market. So we have the stack, we have the queue, we have the set, we have the sequence, we have the map, and within that we have the pair. Am I missing any of them? I will get to that point when we get there. Okay. Stack is what's known as a FIFO data structure, which means that the first element in, stack is what's known as a LIFO data structure, which means that the last element that was entered into the stack is the first one that will be exited from the stack. So last in, first out. If you want to visualize it, you can visualize it as a stack of books in your room. And if you want to get to the book that you want to read, say the one at the bottom, you must first remove all of the books on top. It's a stack. Stacks, and all of these OSU CSE components, for all this, obviously I think they're like common to all of those. The common to all of the OSU CSE components is that they can only store reference types. So you cannot store primitive types in an OSU CSE component. What is the workaround for if you want to store a primitive component in a OSU CSE data structure? There's a trick or a hack, something that Java provides us. Yeah.
Wrapper type.
Yeah, wrapper types. So if you have a little integer and you want to store it within an OSU CSE component, you can use what's known as big integer, which is essentially a wrapper type. So it's a way to have your typical integer, say with a value of 5, but treat it as though it is a reference type. And those exist for all of the primitive types. So there's big integer, big double, big Boolean, big. What would be the last one? Oh, I guess it's just those 4. Okay, so stacks, last in, first out. You append elements onto the stack by using what method? Push. And you remove elements off of the stack by using what method? Pop. All of these, in terms of what they store, is the generic type T. You can think of the generic type T as just a moldable Java reference type that can take on the value of any reference type. So a T could be a big integer. A T could be a simple reader for some reason. A T could be a tree. Oh, I guess we could add XML trees. Or I'll just do trees. Okay. So they all store the generic type T. Now we're going to get to the queue. So if the stack is a LIFO data structure, the queue is a FIFO data structure, which means first in, first out. Meaning that the first element that is added to the queue will always be the first one removed. You could think of this as if you are waiting in line you see a movie, the first person that enters the line will always be the first person that gets to exit the line. Whereas a stack, the first person on the stack is the first one to be removed. On queue and DQ are the ways that you add and remove elements from a queue. All of these have secondary methods, like I'm pretty sure you can flip a queue. I'm pretty sure you can flip a stack, and you can replace front with all of these, which are all methods that we went into. I'll let you digest that while I digest this. Okay. What is the big thing about sets? Sets cannot what? Have what? Have duplicates. Yes. Sets cannot contain duplicates. Another thing that's common between all of these is that they are modeled. So again, this idea of mathematical modeling, modeled by a string of T. Now, when we say a string of T, we don't mean a Java string. Actually, I can actually draw it. We do not mean a Java string, capital S. We mean a mathematical string. And that goes back to, I would look over that slide deck on string theory, just because people forget that a lot. String theory, where you talk about everything looks kind of like this, where you can have a string of integers, and then a stack, a queue, a set, a sequence, and a map, not a map, I guess, can all be modeled by a string of T. Depending on the data structure, the way that you look at the elements might be different. So if you're looking at it like a stack, you might think that this is the front and this is the back, which means that when you add and remove elements, you're doing it here. A queue, you might add elements here and remove them here. A set, it wouldn't matter because a set, to the second point here, does not have a finite ordering. So this mathematical string that I've written up here is the same, if we were modeling it as a set, as this mathematical string here, because we do not care about the order. You must always check for duplicates before adding. Check for dupes before adding. And you have to check that something exists before you remove it, if you're removing by an element. Because you cannot remove something from a set if it doesn't exist in there. What is the method that you can use to just, I'm going to give it away here, but remove any element from the set? What's the method you can use to remove any element from the set? Everybody's laughing, but nobody's raising their hands. Yes, you can use remove any. Sometimes I think I'm crazy. You can remove any, you can use a remove any set. You can use a remove any method to remove any element from the set. So I'm going to draw the set as like just a collection of dudes hanging out. And remove any will randomly pick one of these elements, depending on how it's implemented. Yeah.
Why do you have to check for duplicates before you add them?
Because sets cannot contain duplicates. So if we already have 5, 4, 7, 8, and I'm like, hey, add this 5 to my set, it's going to yell at me because it's going to be like, I already have a 5. Java will crash out.
Oh.
It was part of one of the labs where it was like, you had to implement the version of set that adds all the elements from one set to another. You have to check to make sure that it doesn't already contain the element, because otherwise Java will actually just yell at you. A better programming language would just ignore it, but well, I guess it's good. It's pros and cons. Does not have a finite ordering. All right, I have the penmanship of a 5-year-old. Ordering, which means that these two things are basically the exact same. Okay, those are sets. Sets are fun. All right, sequence is just a sequence of values. So you can imagine it kind of like an array. Actually, you can imagine it exactly like an array. If you want to cheat, you can just imagine it like an array that holds reference types, or that is a reference type. But I guess arrays also hold reference types and is a reference type, but it's a beefed up array. Because you have a bunch of methods that you can use on it. You treat everything like the substrings of a sequence. The big thing for that is actually the big thing in general. All right, it's that I feel like it's important. But for substrings, okay, when you're indexing substrings, especially with strings, so I'll just write Stephen here. When you say that you want the substring from, say, 1 to 4, that is 1 inclusive, 4 exclusive. So I always mess this up. What I do is I write the index locations. Remember, we index by 0. Write the index locations above the string or the sequence and include the 1 and then exclude the include the first and then exclude the last. So in this case, the substring from position 1 to 4 would be P, E, B. I always forget that, so make sure you don't forget that. Same goes for if you're indexing sequences. So if you have a sequence of natural numbers 1, 2, 3, 4, 5, 6, just have index locations 0, 1, 2, 3, 4, 5. And then we want the subsequence of this sequence starting from 2 to, say, 5. That is 2 inclusive, 5 exclusive. So we include 3. And then we exclude 5. That becomes this. I think I mixed them up. But it would be 3, 4, and 5. There's something else that I was going to say in terms of that. Oh, yeah. Anything when you're dealing with insertions. So you can insert elements into a sequence. If you insert by, say, index location 1, that means that the element that you're inserting after you insert it should be the first element. So if we have, say, another natural number sequence, 4, 7, 3, 2, and I say dot insert, I'm going to insert the integer 1 at index location 1. That means that after I do the insertion, 1 should be at the first index location. So 4, 1, 7, 3, 2. And afterwards, you can see 0, 1, 2, 3, 2, 3. It's at the first index location. Okay, that's a lot of the truth. So sequences essentially deal with these sequences of values. I guess that makes sense, but the beefed up array deals with sequences. And you can add and remove by indexing. So as opposed to the queue, where you can only add and remove from 2 separate locations, and the stack, where you can only add and remove from 1 location, and the set, where you can only really add and remove from this disambiguous blob of collective material. Sequence, you can add and remove from any location as long as you have the index value that you want. Okay, those are sequences. They're fun. Maps contain these pairs. Pairs are a distinct link between 2 reference types. Link 2 reference types. They have what are known as a key and a value, or they are what are known as a key value store. So you can have a key where the key is some reference type, and you can have a value where the value is 1 reference type, and they are linked together. Maps store pairs. However, there is a constraint. What is the constraint on maps? Yeah. Yes, no 2 keys can be the same. And if you remember, maps are the one with the disgusting diagram of how everything is stored, because you have this, and then these are your pairs, and then within the pairs, you have two reference types, which are the key and the value, and then these are in and of themselves reference types. When you're working with maps, you use the dot get method, or I think it's dot value, and then you provide a key. Providing the key, and that will give you the value corresponding to the key. You can do that because keys are unique. There's also a dot key method, which will give you a key according to a value, but we don't use that because there can be multiple values. So no two keys can be the same. Vowels can be the same. And those are maps. They store key value pairs. And all of these have methods that I would not memorize, but I would look into. So go through the documentation and look at the kernel methods. The kernel methods definitely, and then probably some of the additional methods, just so that you know what they look like and how they work. Because while you will have the documentation, it's going to be a tough waste of time if you're spending 30 minutes of the exam trying to look through the documentation and understand how the methods work. Whereas if you look at them, say once over the next week, you can recall and you can say, Q has a method called onQ, which will onQ all of the elements of one queue to another. I can use that. Okay, questions on the data structures part of the class? Yeah.
You're like removing something from a key or a stuff. Do I do think input or
So Java has what's known as auto boxing and auto unboxing. So I'm pretty sure, I'm like 99% sure, and I'm grading, so I won't take a point, but if you just call remove and you pass in an integer with a data structure that is storing a reference type, which is a big integer, I think Java will recognize that you want it to basically be a big integer, and you can treat it as such. If you want to be extra sure, you can also just, I believe they have a constructor, which is just new integer, like every other reference type, and then you just pass in the integer value, but it's overkill. Okay, other questions on the data structures part before I erase it all? Okay. Next up, quickly, I'm going to go over that big class diagram again, just because it's an important concept. And then we will talk about recursion. Actually, I'll do recursion first. That was a much more requested topic. Recursive methods, simply put, are methods that call themselves. And typically, you are given a recursive method to implement. It follows, or you have three things that must always be included. In terms of the tip that I always give, which is that a recursive method, one that calls itself, there's three things that you always need. You need a base case. So you must always have a point at which the recursive method should stop calling itself. Because we actually learned this very recently. Every time you call a recursive method, it adds the stack trace onto the stack and starts a new execution. Every time you recursively call, it starts a new execution. And if you keep doing that and you don't have a base case, Java will call recursive versions of the same method, allocating new memory for all of the variables that are needed for that method. And eventually it will run out of space and it will overflow, and Java will get very angry at you. It's a Stack Overflow error. So you need a base case. In order to get to that base case, you must make the problem smaller. And typically, the problem that you are making smaller is going to be what you are passing into the recursive method. So if you have, say, foo, which is taking in a natural number, the thing which you are making smaller is, I don't think I'm not gonna say 100% of the time, but like 99.999% of the time, it's going to be that natural number which you have to make smaller. And that natural number is going to be what is looked at as your base case. So if we have foo2 and we're taking in a string, then that string is what you must be making smaller throughout the method body if you want to make sure that you eventually hit your base case. So these two should always be linked to the argument that's passed in. Which makes sense because all of the other variables are localized to each recursive call. So the only thing that is being passed, the only thing that could potentially be changed is what's being passed in. If you have foo3, which is taking in like a double, it's that double which eventually must reach the base case. And then the third one is that you have to recursively call the method. Please look at the instructions. Oftentimes, or sometimes, you will get a method and it will say something like, do not use recursion, it is not needed. And then some people will try to use a recursive method. And I'm instructed to give like 0 points on that, on like the rubric. So just read the instructions. And then there are some methods where it's like, you must use recursion, and people try to do it iteratively. Don't do that either. Follow the instructions. But besides that, some tips for recursive methods. Almost any recursive method that uses a natural number is going to follow the form of divide by 10, do something, multiply by 10. And then you have your recursive method somewhere in here. If you look at all of the natural number recursive methods that we have made you guys write over the course of the semester, you will find that I'm pretty sure every single one of them follows this example. So pattern match, if you have a natural number recursive method, it should follow this form. For string recursive methods, this is for nothing. String recursive methods are typically taking a substring, doing something, calling your recursive method, and then concatenating strings. These ones show up less often, but still exist. And the third one I will say is tree. Oh, we didn't go over trees. We can go over trees. But for tree-based recursive methods, this one, almost every single one follows the same pattern, which is if it's a leaf, do nothing, else, loop through, else do something, loop through all children, recursive call. Almost every single tree one follows the same exact structure because that's how you can easily do recursion on trees. But besides that, it's just practice, 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 and then looking at the different recursive methods. There's not too many things, too many recursive implementations that can be asked of you about a natural number or a tree that don't somehow just end up repeating themselves. Okay, questions? Okay, we'll do trees. Trees are fun. Trees are just a collection of nodes. Ding. And they're also a recursive in nature. So you have a collection of nodes here, and each one has maybe some children. I would look at the terminology too, because it's important to know the terminology. This is the root. These are what are known as leaves, or this is a leaf. This is the child. This is a sibling. And then if you want to go that deep, you can say that this is a grandchild. The size of the tree is 1, 2, 3, 4, 5, 6, 7. The height is a longest path from the root to the node. So in this case, it would be 3. The length of any specific path is including the nodes that are given. So if this is, say, A, B, C, and I wanted to say what is the length of the path from A to C, it would be 2. And the last thing to mention is that this C, while also being the child of the A node, is in it of itself a tree with its own collection of nodes and children. It's a size 3 tree. It's a height 2 tree. And these are children of the C node, grandchildren of the A node. But it's its own tree in of itself, separate from all of the other nodes. Trees manifest in the fact that we use them for XML trees, which is for storing documents. XML trees are a little bit different in the fact that nodes can be either a tag node or a text node or a content node, if you will. Content nodes do not have children. Tag nodes may or may not have children, and there are a bunch of methods that help you determine that, such as isTag, dot label. Remember that dot label will return the label if it is a label node, or it will return the text if it's a content node. So you can call it on both a tag node and not a tag node, but what it will return is different. Attributes of a XML tree node. There we have attributes. And it has an attribute called time, which is like 905, and space, which is like 4 megabytes. Every attribute is stored as a pair, if you will, of 2 strings. So it might look like, let's say that instead of space, this was just 4. So if you were given this and you were asked, what is the Java value of the space attribute? You might want to say that it is an integer, but it is not. Everything is stored as an int or as a string. You should use the method hasAttribute to determine if a tag has an attribute value named, say, time or space. And then you can use the method attribute value to actually get what the value of the attribute value named time or space is. Okay. Any questions on anything I just said? There's a lot. Okay, that's trees. What other topics do people want me to go over? I'm trying to think of things that are interesting, but I'll go over pass by value versus pass by reference because people still forget that there is a big difference between the two. Pass by value, remember, when we're talking about primitive types, or we're passing primitive types into a method header, they are passed by value, which means that you just take whatever the value is that you're passing in and you copy it into the method. So we're going to have 2 examples for this part. We're going to have foo1, which takes in an integer n, and we're going to have foo2, which takes in a natural number. We'll call it x. And then we're going to have our main Java program where we set, say, int m equals 4 and natural number y equals new natural number 4. And then what foo and foo2 do, they're very interesting methods, but this just calls x dot increment. And you can imagine this just calls n plus plus. So let's actually draw what happens here. When we are here, we draw m as a primitive variable, which means that it is stored directly where the name is stored, like that. Y, however, is a reference type, meaning we point to the actual object value. That's actually important terminology alert there. The thing that we actually care about is the object value. So in this case, 4. The thing that we don't really care about, or where the reference is stored, is called the reference value. Okay, cool. So this is what it looks like. Then let's say we call foo1 and we pass in m. What happens is that we go to foo1 and it says, hey, we need an integer n. Since it is a primitive type, we copy, or we just pass the value in. In this case, n gets copied as m is 4, and then we call n plus plus. N becomes 5. The method ends, and we don't return anything. These are both void methods. And so n gets deleted by Java's garbage collector. And m remains as 4 because we did not pass a reference location. Now, on contrast, we call foo2 and we pass in y. This time, since it's a natural number, we are passing by reference. And so x gets initialized to the object value where y is pointing. So now we have 2 reference locations pointing to the same object value. This has a name. Does anybody remember what the name is? Aliasing. Yes, this is aliasing. And aliasing is dangerous if we are storing what types of values? Mutable types. And what does mutable mean? Yes, exactly. 3 for 3. Aliasing is dangerous if you're storing object values that can be changed. It's not that important if you have something like a XML tree or a simple writer where instance methods cannot change the object value of that type. But natural numbers are a mutable type, meaning that we can update the object value of it by calling methods like increment or multiply by 10 or divide by 10 or add or subtract or divide. We can change the object value of the natural number, which is what we're doing here. So we call x.increment. We follow the map to the object value. We increment it. And since it's a void type, we don't return anything, meaning that x gets deleted by Java's garbage collector. But the damage is done. Increment has been called. Y now points to an object value of 5. Does that make sense? The biggest tip I can give is please just draw pictures. I want to see a lot of pictures on the final because it will help you not make mistakes in pass by value versus pass by writing. Okay, we've got like 10 minutes left. Does anybody have any questions? Otherwise, I can stay here for actually probably not too much longer, but talking about CSE 2221. Yeah.
If you do like a simple recursive tracing tape.
Mm-hmm. Yeah. Let's just pull up the one from Bitzer. Is that okay?
Yeah.
Okay. If it was on the midterm, I think it was. Okay. Actually, I'll just change it. So if we have private, I'm not going to draw it, but we have a method called increment, which takes in a natural number n. And the contract for increment is that it ensures n is equal to the old value of n plus 1. And we start with n equaling, say, 7, 3, 0, 5, 0, 0, 0. Okay, so like I said, the first thing that you always do is usually a divide by 10. So int ones equals n dot divide by 10. So afterwards, and if you remember, divide by 10 just chops off the right out value. So we have 73050, and then we have ones is equal to just 0. Actually, I'm gonna make this 9, just so that it's more interesting. Okay. Now we increment ones, so ones plus plus. So now ones is equal to 10 and is equal to 730,500. Now we get to our if statement. So if ones is greater than 9, meaning that it is 10, then we have to do something. So in that case, everything is going to just stay the same, at least for this one. 730,500. Ones is 10. And we reset ones back to 0. Ones back to 0. And is 730,500. Ones is 0. Okay, now we're going to take a portal up here because I ran out of space. Here's where the recursive call comes in. We call increment on n. I'll redraw these up here. So n before the recursive call was 730,500 and ones was 0. After we call increment, the only thing we do is we take n, we look at what the contract of increment does, and we update it accordingly. So n should be the old value of n plus 1. So 730,500 afterwards should just be 730,501. Ones is still 0. And finally, we call n dot multiply by 10 and add ones back, which will make n 730,501. Ones equal to 0. Does that make sense?
Yeah, so you only write it once at the very end.
Only write what ones?
Right, the thing I missed on the midterm was the formatting.
Yes. So there should only be one thing throughout the entire tracing table.
Okay.
And a good way to check is, I mean, if it's called increment and the value at the beginning is 7305009, your value at the end should probably be 7305010. So you can use that to spot check your work. It's just by looking at the method contract and making sure that your values line up. Okay. Does anybody want the next or the last question? Otherwise, I'm going to draw that diagram again. Yeah.
Can you go for the animal class, number 3.2 and the meat?
Yeah. Okay. Yeah, let me pull that up. So this has to do with method overriding versus overloading. If I can open up. All right. Actually, I'm going to plug my laptop in for this one, just so I don't have to write all of the code. Because I'm lazy. Okay, so if you haven't taken a look at the sample final yet, we have this class animal, which introduces a make sound method, a void method, which just prints out some generic sound. And then we have a class dog, which extends the animal, overrides this method bark or make sound, and has it say bark instead. So if we were drawing the class diagram here, we would have that we have the animal class, and then extending that animal class is the dog class. When you extend a class in Java, you automatically inherit all of the methods that are already in the animal class, and you can define more methods. And any method that is in the animal class that you don't like the implementation of, you can override like that. So when we make a animal, my animal equals new dog, we're saying that my animal should be a reference type to a dog, in which case I'll just write dog. And then we're saying my animal 2 should just be an animal. And then we're saying my animal dot make sound. So when we do this, we go to my animal and we look at what the dynamic type of the class is. So you have your interface type here, which is the interface, and then you have the implementation type here, which is an actual Java class. When I say actual Java class, I mean a blue circle. So in this case, there would be, I didn't draw the full diagram, but there should be oh wait, these should be circles. Animal class, dog class, and these should both implement from some animal interface. So since the dog extends the animal, which implements the animal interface, that's why we can define a dog using the animal interface. So we say that my dog should be an animal. And when we call my animal dot make sound, what it looks like, what it looks at is it looks at the dynamic type of the class. So it's going to look at the fact that my animal is a dog and my animal 2 is an animal. So my animal dot make sound is going to print out bark because it's a dog. My animal 2 is going to print out some generic sound because it's an animal. So always look at the dynamic type of the method or of the class. Okay. Other questions? I saw somebody had their hand over here.
The final, this week and GUI stuff as well.
It's going to cover GUI stuff, but only in like probably like a multiple choice or maybe a short answer. It's not going to be like you're writing. Yes, it will be entirely conceptual. Loop invariants are going to be on the exam, yes. At least I'm like 90% sure. Okay. Any last minute questions that you can get off in 2 minutes? Yeah.
Besides like the practice final, what would you suggest we do for like practice problems?
I would at least try to write some code without an IDE because people always writing code without an IDE is like so annoying. So I probably have some extra sample recursive methods that I can give out. Do those, but don't do those in the Eclipse IDE. Like sit down and actually write it and then type it into Eclipse and see, oh, I made a syntax error here, or I didn't use this method correctly. I spelled it wrong. Because people always forget that. But besides that, just look at every single slide and every single lecture and every lab and every project and everything. A good like litmus test is you should be able to go through any of your projects, like pick one at random, and you should be able to look through each line and you should be able to explain exactly what it does. So set 1L, test set equals new set 1L. You should be able to look at the concepts of that and be like, oh, so this is like the interface type and this is the dynamic type. And that means that it implements the set, which contains a bunch of contracts for like a bunch of set methods. And then I can use those methods because I'm using set 1L, which is an implementation of that class. And like each line of code in Java can give you like, you can probably get to like 90% of the concepts in the class from a single line of code, just because everything's connected. So it's like a graph data structure we didn't talk about. Okay, any other final questions? Okay, good luck. You guys will be fine. Yeah, I'll see you guys next Wednesday, 8 a.m. It's gonna be a party. No, everybody gets attendance today.